Hello everybody, and welcome very much to this webcast on posture and movement prediction with inverse dynamics. My name is John Rasmussen and I am the presenter, and you can see my face here on the left hand side, and on the right hand side you can see the face of my colleague Arne. He is the host of this event, and he is sitting here right next to me trying to keep track of all the technology involved in this webcast presentation. Furthermore, we have with us Søren Tørholm and Michael Damsgaard. Their role in this game is to try to answer the questions that you may have as we go along. One of the advantages of doing webcasts is that you are able to ask questions during the presentation without disturbing me. And if you want to do so, please notice the lower right-hand corner of your screen, which you can find a question mark. If you click the question mark, a small question and answers panel will pop up, and you have the opportunity to type a question into that question and answers panel. Before you submit the question, please make sure that you submit it to host, presenter, and panelists, and not only to the host, because this will mean that Søren Tørholm and Michael Damsgaard will actually receive your question, and they will try to answer it as we go along as well as they can. We may decide to postpone some of the answers to the end of the session, and then I will give the answers orally here in the presentation. At this time, we usually take a small break. It's a little early for a break, I know that, but just to help those of you who have not been able to set up the audio, to give you one final chance, those people who cannot hear me can see the sign on the screen here, and they have the opportunity to go in and see the instructions on how to set up the audio. Fortunately, this is a recurring problem with these WebEx presentations, that people do not get the audio set up. You just leave the sign on for a few seconds, and I thank you very much for your patience with this. Thank you very much. Okay, so we have divided this into three easy parts. The first part is about background and methods, and let's go right to that. The background for this work is that we have increasingly detailed and reliable musculoskeletal models. Those of you who already know the technology that we're working on, you also know that we're making models like the one that you can see on the right-hand side here. This is a model of a seated car driver, and comprises a lot of muscles, actually several hundred muscles. So these models are attaining a very high level of realism. Now, having these models, we want to exploit the potential of the models, and we expect to do that by reducing the need for doing biomechanical experiments in the future. So if you were designing something that's an environment which would be in conjunction with the human body, and you wanted to change the parameters of that environment, then ideally we would like the model to be able to tell you whether you were going in the right or the wrong direction. Now, sometimes the environment influences the way that the human is behaving in that environment. So we would like to be able to foresee what different types of movements that the human body would take when we change the environment. Now, since we are doing inverse dynamic analysis here, we are faced with the fact that we must use as input the movement, so we must be able to predict how the human body will respond in terms of movement to a change in the environment. Otherwise, we are still stuck having to do an experiment every time we change the environment. So those of you who know inverse dynamics, you also know that it's usually perceived as something that requires posture or movement as input, and also, in addition, all external forces. This means that the synthesis of movement is something that people who have been reading the biomechanical literature usually are perceiving as affiliated only with forward dynamics. And those of you who know the literature, you also know an outstanding example by Anderson and Pandy, who have been synthesizing an entire gait cycle. Gait is a rather complicated movement, and they have been doing that with forward dynamics based on a performance criterion. Probably this is one of the reasons why people feel that forward dynamics is the only technology that can actually synthesize movement. But it turns out that this is not the case. It turns out that inverse dynamics can actually compute interface forces between the human body and the interface. So it is not necessary to have all external forces as input. Believing that this is necessary is a popular misconception, and we can address that at some other webcast. I'll not go into detail with that here, but it is actually not the case. Inverse dynamics can also compute the forces between the human body and the environment. It's also a popular misconception, as I said before, that inverse dynamics cannot synthesize movement, but it actually turns out that it can. This is actually the focus of this presentation. Furthermore, inverse dynamics for this purpose may be more computationally efficient than forward dynamics, and in fact in just a moment I'm going to show you an example which we can run right on the fly here as you're watching the presentation, and which will be able to predict a bicycling movement. Before we get that far, let me just introduce the way we do inverse dynamics, and I apologize in advance for this very complicated slide that you see here. We're leaving it in the presentation here because we're going to email the presentation to those of you, to every participant in this webcast after the webcast is finished. And so if you don't get all the details here, you can go back and have a look at it afterwards. But what we do in AnyBody is we do 2 rounds of analysis. We put kinematic boundary conditions and the constraints of joints, and also the imposed movement into a kinematic solver. And the kinematic solver will then give us position, velocity, and acceleration of every segment in the system. To this information, we then add external forces and kinetic boundary conditions, and we form the redundant equilibrium equations, and then we run the second round of analysis, which is the solution of the redundant equilibrium equations. And we do that by means of optimization, which means that we're able to handle the redundancy. Again, the way to do that is the subject of another webcast, and I will not go much into that today. The bottom line is that out of this analysis comes the muscle and the joint forces, and also the forces between the human body and the environment. So this is a simple inverse dynamics analysis as it takes place in the AnyBody modeling system. So the question is, how can we synthesize movement out of this system? What we do is we add a loop to this whole analysis. And the loop looks like this. We take the standard output from the inverse dynamics analysis, the muscle and joint forces and the interface forces, and then we do some amount of post-processing, which will give us a performance criterion. Now we are going to discuss later what that performance criterion might be. And using the performance criterion, we will do an optimization. And if you're interested in optimization technology, I can mention that the algorithm that we're using is a feasible directions algorithm. And there's a long explanation behind why that might be a good idea. Actually, it works very well for our kinds of problems. Now, this optimization then, based on the performance criterion, tries to come up with an improved movement. So it feeds an improved imposed movement back into the system, and we do a repeated analysis, and we come out with a new performance criterion, and then that loop continues for a number of iterations until we come to a point where we have convergence. And at that point, we will have optimized the movement or the posture of the system. In terms of formulation of this optimization problem, we can think of a number of different ways to formulate it. The first way of formulating it is the most obvious one, and the one that you see here. This would be the design optimization formulation for an ergonomics problem. In this case, we can imagine that we have an environment which is somehow parametric, so we have a number of parameters that determine what the environment would look like. That could be, for instance, the parameters of a CAD model of the environment. And so we have here the environment as the variables in a minimization problem. Minimization will optimize or minimize, in fact, an objective function f, which is our performance criterion. And this function f is then a function of the environment, and it's also a function of the posture or the movement of the system. And in the present case, we are only changing the environment, and then we are keeping the posture or movement the same, independent on what the environment looks like. Now, another way of formulating it would be to do a posture or movement optimization. In this case, we optimize the posture or the movement, and then we keep the environment fixed. So that would be the other extreme. We're not changing the environment, but we're just trying to figure out how the human body is performing in this given environment by optimizing the posture or movement. And then finally, we can think of a combined optimization problem, which is really what we want to do. And the combined optimization problem is one in which we optimize the posture and the movement along with the environment, so that when the environment changes, we also allow for the optimizer to change the posture or the movement such that it fits the environment as well as possible. And this would really be the kind of problem that we are looking to do. Please notice here that we have the posture and the movement separate, and also up here in the list of variables we have them separate, but we are using the same optimization function, the same objective function for the posture and the movement and the environment. So it's necessary here to make the assumption that it is the same performance criterion that would give us a good environment and also would govern the way that people would be moving in that environment. That is a rather strict requirement on this type of problems, and it is really necessary to come up with such a function in order to do the optimization. So this combined formulation will only work if we can find a reasonable objective function that will work for both of those classes of design variables. We have some results that we have published actually several years ago. The first one I'll show you here is a 2D model of a squat jump that we did back in 1999 for European Society of Biomechanics conference in Dublin. And it's a very simple model. We have just 9 muscles in each leg, and the movement prediction is to do a squat jump. So it's really easy to say that the objective function of this would be the height of the jump. So we simply want to jump as high as possible. You can see over here in the figure that we have introduced 3 angles, x1, x2, and x3. These angles are all functions of time. So we're trying to use as design variables 3 functions of time. In order to do that with mathematical programming, we must discretize those functions into a number of discrete parameters, and the way we have chosen to do that is by means of Hermite polynomials. Again, I will go very quickly over the definition of Hermite polynomials, but it's a special type of orthogonal polynomials which will ensure that each new term you add to the polynomial will give you something that you do not have in any of the other terms. And this gives us, when we then use the coefficients of the terms in the polynomial as design variables, it will mean that each design variable adds something unique to the function, and that is a nice quality to have in an optimization problem. So the objective function here is, as I said, to maximize the jump height. And I really wish that I could show you the results, which is an animation. Unfortunately, the webcast technology does not allow me to do that. But if you look here at the bottom of the screen, you can see that I have written a web address. And if you're able to have a browser window next to the webcast, then you can open that up and you can go to this example that I have, this URL address that I have shown here. And then you will see an animation of the squat jump before and after the optimization. I'm going to switch the slide now, but the same address will be on the next slide as well. So the address is on the next slide here. This is the same address. So if you have the opportunity, please go to that address and see what the movement looks like. The model is the one that you see here on the left-hand side. It's 2 legs, but it's really a tactical plane movement. And the optimized movement very closely resembles movements that you can find in real life, and also the optimized ground reaction forces that we get out and which are computed automatically by the system. They closely resemble measurements that you can find in the literature, for instance, in the many papers by Gobert and Fenimichenau on squat jump. The initial jump height of the proposed initial motion is very, very low, a fraction of a millimeter, I think. And the final jump height is 123 millimeters. So obviously it's a big improvement, but it's not a very impressive jump. And I'm sure that if we used a more complicated leg model, then we would be able to make it jump higher. The second example that we have done before is a pedaling example. The model that you can see here on the right-hand side is a simple 2D bicycle model. It is equipped with the same muscles actually as the squat jump model. So it has 9 muscles in each leg. So it's a pretty simple model, but we know from comparison with experiments that it captures the physiology and the muscle recruitments of a bicycling process fairly well. Making some assumptions in this bicycle model. We are presuming that there's a constant crank velocity. We're presuming that the pelvis is fixed to the saddle as opposed to having an upper body on the model that would attach to the handlebar. And we are constraining the mechanical output so that the model has to deliver a certain amount of watts on average on the crank. Then we're using as variables the crank torque profile and the ankle angle variation. That was what we did in the publication about this, which I will refer to in just a moment, and which you can find on the Anybody Research Project's homepage in the publication list. However, in the example that I'm going to show you now, I would like that to run very quickly, so I have restricted myself to just look at ankle angle variation. So let's try to do a simple demo of this. And what I'm doing here is I'm opening up the Anybody modeling system, and I'm going to single step through one analysis of this model. And I'd like to ask you to pay attention to the variation of the ankle angle as the model is moving. Oops, that was the wrong button. I was supposed to single step through the movement. I will do that now. You can see now the pedals are moving in small steps, and you can see that the muscles are bulging as they are being activated by the system. You can see that on the leg that's going down here, you can see a lot of quadriceps activity for extending the knee. But please notice the ankle angle. The ankle angle is being kept constant in this bicycling process. I'm just going to do a few more steps. And you can see now the right leg is changing from the downhill stroke to the uphill stroke, and you will also see the muscle activation pattern is changing from the forward side to the backwards to the posterior side. And so that was the entire analysis. I'm then going to open up a window in which we can look at the results of this analysis. The first piece of result that I'm bringing out is the ankle angle. It is, as you can see, it is completely constant. And the reason why the ankle angle is completely constant is that inside the definition of the model, I have specified that the ankle angle should have no variation. Where this is defined in the model is in this section, the bike parameters at the top of the model. And this, just to introduce what this is to you, this is not C++ or JavaScript or something like that, although it looks like it. This is the AnyScript language which we're using to make the biomechanical models in the Anybody modeling system. And you can see here that the foot angle amplitude and the foot angle phase shift are both 0 in this initial configuration. And what this translates to in the model is that it keeps the ankle angle constant. If I go down a little bit into my definition of the file here, we come to a section called the study. Inside the study is defined operations that we do to the model. And I want to draw your attention to one particular thing, which is this output function, which is called maxAct. And it has a value which is equal to the maximum muscle activity. Go back to the chart view where we can make graphs. Then I will be able to find this property in the study. Here you see the maximum muscle activity, and you can see how that varies over the cycle, and you can see a very characteristic peak here in between the two major peaks, and this peak is coming at the point of the dead center of the pedaling movement. And actually this peak is not something that you usually find in experiments. If you take EMG of the muscle activities, you will usually not find this peak. And the reason why we have this peak here is because that we have specified that the bicycling process should be done with an unnatural kinematics, namely with this constant angle. So what we're going to do in the model is we're going to specify an optimization problem, and that takes place a little bit further down. So in the section that you see on the screen now, you can see that we have specified an optimization problem in which we have two design variables. The first variable is the amplitude, and this is then linked to the parameter that we saw at the beginning of the model, the foot angle amp. We also have the phase shift, which is linked to the foot angle phase that we also saw in the beginning of the file. And then finally down here we have defined what we call a test measure. This is actually the objective function of the optimization. So we've said that what we want to minimize is the maximum of the maximum activity over all the muscles. The maximum activity over all the muscles is really the envelope of the muscle active states. And so that means that it is the highest activated muscle at any point in time in the cycle. If we can lower the maximum of the maximum activity, then it means that we will have enabled riding the bicycle with a lower effort than we have at the present time. So we are basically here making the assumption that when the bicycle rider is choosing his or her movement of the ankle angle, then he is essentially trying to make life easy for himself, meaning that he's controlling his ankle angles in such a way that he minimizes the effort of driving the crank around at the speed and crank torque that we have specified. To run the optimization, I can go down here in my study tree, the optimization, and I can click run. And if I did that, the bicycle would start pedaling like crazy, and you would see that the ankle angles would change gradually. Unfortunately, we cannot do that over the webcast because it generates much too much graphics to be transmitted over the internet. So unfortunately, I have to switch the graphics off as we run the optimization. So now the graphics is switched off, and I click the run button. Number here where I have my cursor, which is counting up from 0 to 1 to 2. And every time that number increases, it's because the analysis has taken another iteration, and it has to count up to 6 or 7 or so, and then we will have convergence, and the system will have identified a different movement of the pedals from what we had before. And we will go back and have a look at what that looks like. So I think it's just about finished now. In just a few seconds, it will have counted to 6 here on my screen. Or maybe 7, I'm not quite sure how far it has to go. Now it's finished. And we can go back to the analysis again. Dynamic analysis, switching on the graphics once again. And then I will single step through the movement and try to pay attention now to the ankle angle variation. see here now we have a dorsiflexion of the first foot, so now the ankle angle is no longer constant. Now this foot is, now the ankle is extending into plantar flexion. And you see we're now at the bottom of the cycle and we have a considerable plantar flexion in the model. And here we have finished the analysis, and I'll try to call up the window with the graphs again. And you can see here the maximum muscle activity. We no longer have that little peak around the top and bottom dead centers. And if we want to study in detail how the ankle is moving, we can do that as well. You can see here that the ankle is now moving as a nice sine function. So the optimization has caused the initially constant crank angle to attain a certain sinus-shaped variation. Just open up another window here to examine the convergence of the optimization problem. And so in this window you can see how the maximum muscle activity has been decreased by the optimization from 1.35 or so and down to 1.21. So this is a considerable reduction of the maximum muscle activity and thereby a reduction of the effort of the bicycling process by means of doing this optimization. So you can see that we can actually reproduce the real ankle movement very nicely by this optimization. And you can also see that the numerical efficiency of this is actually quite high. It doesn't take a lot of time to do that. Furthermore, I have not demonstrated that here, but we have done experiments with these models. And it turns out that it is very important to choose the right objective function, of course, but several different objective functions which could be deemed reasonable for a problem like this will actually produce the same results and pretty much the same ankle variation. So whether we use maximum efficiency or minimum fatigue or minimum effort as we use now, or we use an optimization problem formulated as minimum muscle trauma, where we compute the muscle trauma as a damage accumulation function, we will in all cases come up with the same results with an ankle angle variation that resembles quite closely what a real bicycle rider is doing. So perhaps there is some hope in this method, in the sense that you do need to pick the objective function reasonable, but if you do pick it reasonably, then maybe it's not so important precisely which objective function it is. Now, the second part of this presentation is about the more complex models that we have available now, because the examples that I've shown you so far are with very simple models. We now have much more detailed models available, as you can see in the picture here. And obviously, we would want to apply this optimization to some sort of daily movement. And we have this dream of eventually being able to do egress out of a vehicle. But we're starting with some simpler examples on these rather complicated models. And the first example that we will look at is the standing posture prediction. So this is just an example of quiet standing on two legs. And we're trying to figure out how the body would move about its different segments and adjust its joint angles so that we stand with a minimum effort. Our initial guess of the standing posture is one which is symmetrical, and also we have specified that the model should remain symmetrical. And then we have also specified that the center of gravity of the model should be positioned exactly vertically above the ankle angles. The reason why we have picked that is that if we do that, then of course we reduce the torque about the ankle angles to zero. And in some sense, if you want to minimize the muscle effort, that might be a good idea to do. And then we use as design variables here, we use the ankle angle, the hip angle, the angle between the pelvis and the thorax, use the glenohumeral flexion and the glenohumeral abduction as design variables, as postural design variables. And again, we use the same objective function as before. We are minimizing the maximum muscle activity in percentage of maximum voluntary contraction, and this translates to a minimum fatigue optimization. So what are the differences then? Well, on the left-hand side here, you see the initial posture, the one that has zero moment about the ankle joint. And on the right-hand side, you see the optimized posture. And you can see that we have been able to reduce the percentage of maximum voluntary contraction from 23.2% down to 19.8%. It's not a very big reduction, but probably it is significant. You can also see that it looks like the muscles are actually more active on the right-hand side than they are on the left-hand side. But remember that what we've been trying to do here is to minimize the maximum muscle activity. We're not trying to minimize the sum of muscle activity or something like that. It's just the maximum muscle activity. This means that, for instance, on the left-hand side, you can see that the muscles in the legs are very relaxed because we have the center of gravity exactly above the ankle joint. But in the picture on the right, the hamstring muscles and also the gastrocnemius muscles are quite active. And this is because the model has taken the opportunity of moving its center of gravity a little bit forward, so that the center of gravity is now somewhere above the midfoot rather than right above the ankle joint. And of course, this means that the plantar flexor muscles will have to carry some additional load here. But as long as the load does not get higher than the relative load that we have in the upper body, is quite okay. And it turns out that by leaning a little bit forward like that, it's possible for the body or the model to save a little bit of the effort that it has to use in order to keep its upper body upright. And so finally, it turns out that this can reduce the the percentage of maximum voluntary contraction a little bit. And it is actually also consistent with what we find in experiments, that the center of pressure is not right below the ankle joint, but actually a little bit forward compared to that. We've been trying to do also an example that predicts posture in a sideways fashion. And we've done that by hanging a shoulder bag with a weight of 10 kilograms on the model. You see the shoulder bag here in these two pictures. Again, on the left-hand side, you have the initial posture, which is a completely symmetrical posture. And on the right-hand side, we have the optimized posture, which again is leaning a little bit more forward than the other one. You can't see that here because we see it directly from the back. Actually, this one is also leaning a little bit to the left-hand side. Of course, this is leaning against the weight of the bag. It's just very difficult to see in this picture because the bag is not heavy enough. So if we use a heavier bag, if we increase the load of the bag to 30 kilograms, it becomes more obvious what's happening. Here you see the results for a bag of 30 kilograms. The initial posture on the left-hand side, we're now using 50% of our strength to carry the bag. And on the right-hand side, you can see that this can be reduced to 45% of our strength if we are leaning a little bit against the load of the bag, so that if we have the bag on the right-hand side, then we are leaning a little bit to the left in order to compensate the weight of the bag. This all seems very intuitive to me, and it looks like a reasonable result. But I have to admit that we have not validated this experimentally. Now, the final part of the presentation is, of course, the conclusions. And, just to sum it up very quickly, I would say that it seems that the method is working if we know what the criterion is. And that was the case in the squat jump example, where it was very clear that the criterion would be to maximize the jump height. We've also seen in the pedaling example that we can get similar results by using several different reasonable criteria, and we're getting so it looks like maybe there's some flexibility in the way you define your optimization problems, as long as the criteria that you're using makes some amount of sense from the point of view of physiology. And Then we've been doing some posture prediction based on minimum fatigue with the shoulder back and standing model, and we are getting reasonable results from that, but we still, of course, need to do further validation of that. We are establishing cooperation with some of our scientific friends who are doing extensive experimental investigations of models like these, and we're going to try to hook up our models with their experimental results. Hopefully we can get some clarity out of that. We are also very eager to try on more complex movement predictions such as egress, and we will do that sometime in the future. Finally, let me point you to some of the online resources you can look at if you want to know more about this. I'll say again that we're going to email the presentation to all of you as a PDF file, but you can also find other information on the web. At Anybody Technologies homepage, you can download the software that we are using to run these examples, so you can play around with your own examples. It is a commercial software system, but you can get a free demo license that will run for 30 days, so you do have a little bit of time to play around with it. You can also find tutorials and documentation here, and you can find also a tutorial on how to define the optimization problems. So finally, this webcast will be recorded and will be available for replay from the homepage at a later time. The Anybody Research Project is our academic branch, and from its homepage, anybody.aau.dk, you can find the public domain body models that we're using, and you can also download many of the publications about this technology. So